Your immune system is one of the most sophisticated defense forces ever built. It can identify an invader, a virus, a bacterium, a mutated cell, and destroy it with extraordinary precision. In fact, your immune cells do this thousands of times every single day. So here's the question that stumped scientists for decades. If our immune system is so powerful, why does cancer so often win? The answer comes down to something called immune checkpoints. Think of your immune system like a high-performance engine, incredibly powerful, but with a built-in governor to keep it from redlining. These checkpoints are molecular off switches on your T cells, the immune system's frontline soldiers. They exist for a good reason. Without them, your immune system might attack your own heart, your kidneys, your brain. Checkpoints are biological safeguards, and cancer figured out how to use them as a weapon. Here's how it works at the molecular level. On the surface of every T cell sits a receptor called PD-1. PD-1 is short for programmed Death 1. When it locks onto a partner protein called PD-L1, it sends a signal. It says, "Stand down, nothing to see here, you're not needed." In healthy tissue, that's a crucial message. It stops T cells from attacking your own organs. But many cancer cells have learned to drape themselves in PD-L1. They wave this molecular white flag, and your immune system backs down. The tumor grows, unchallenged. There's a second checkpoint that operates even earlier, before T cells are fully activated at all. It's called CTLA-4. Think of activating a T cell like starting a car. You need two things, a key in the ignition and a green light on the dashboard. CTLA-4 acts like a counterfeit key. It competes for the same activation slot, and when it wins, you get a stop sign. It never fully powers up. Cancer exploits this too, keeping T cells perpetually parked. This is where checkpoint inhibitors come in. They are precisely engineered antibodies. These large Y-shaped proteins are designed to physically block these molecular interactions. Block PD-1 or PD-L1 and you rip away the tumor's disguise. The T cell stays active, the brakes come off. Block CTLA-4 and T cells that were stuck in neutral finally fire up and join the fight. Today, 7 major checkpoint inhibitor drugs are approved by the FDA. Pembrolizumab alone, brand name Keytruda, is approved for over 40 cancer types. Nivolumab is used for melanoma and lung cancer, while atezolizumab targets bladder and triple-negative breast cancers. Durvalumab is used for biliary tract cancers, and avelumab for Merkel cell and bladder cancer. Ipilimumab and tremelimumab are the leaders in CTLA-4 inhibition for melanoma and liver cancer. Scientists discovered something even more powerful, removing both brakes at once with combination therapy. Combining a CTLA-4 and a PD-1 inhibitor creates a response that can defeat tumors resistant to either drug alone. The trade-off? The immune system can overshoot. Side effects like inflammation become more common and intense. Checkpoint inhibitors are transformative, but they aren't a universal cure. Only a subset of patients respond. Factors like tumor mutational burden matter. More genetic mutations make cancer more visible to the immune system. PD-L1 expression and MSI high status are also key markers that help predict how well a patient might respond. Finally, the tumor microenvironment can build a fortress that dampens even the most reinvigorated immune attack. In 2018, the Nobel Prize was awarded to James P. Allison and Tasuku Honjo for these foundational discoveries. Before these drugs, metastatic melanoma had a median survival of 9 months. Today, many are alive 10 years later. That is not incremental progress. That is transformation. Checkpoint inhibitors simply taught the immune system to stop holding back. For more science breakthroughs, visit unbedsidemanners.com for more stories. Subscribe below for more.